Boeing turned a simple upgrade into a program that has cost the company roughly $15 billion and pushed entry into service back by about 7 years, with a single $4.9 billion charge booked in 1 quarter. That number is not a rounding error, it is the financial scar from concentrated technical risk. This is not a story about a single broken bolt, it's about a design philosophy, a handful of high-stress subsystems, and how a cascade of engineering fixes, inspections, and certification pauses can turn a low-risk plan into a multi-billion-dollar crisis. But here's the catch. Boeing didn't build a clean-sheet airplane. It tried to upgrade a proven platform, keep pilot commonality, reuse systems, and add a huge new wing, a new engine, and folding wingtips. That choice concentrated risk into a few novel parts. The result? When those parts misbehaved, everything else stopped. Start with the hardware everyone talks about, the GE9X engine and the folding wingtips. The GE9X is a step change in thermal and mechanical stress compared with previous engines. It uses advanced materials like ceramic matrix composites and very high pressure ratios to squeeze fuel burn down. That's great for efficiency, but it also means new failure modes and new inspections needs. When components run hotter and spin under higher loads, small wear patterns can grow faster than expected. So the engine required more intrusive borescope inspections and targeted on-wing checks during testing. Those inspections are not a one-day fix, they change maintenance cycles and fleet availability. Look, let's be real. Pushing the envelope on materials and thermodynamics always buys efficiency and the cost of unknowns. The GE9X's innovations were always going to need service data time to mature. The surprise was how much that learning curve would slow certification and delivery. Then there is the folding wingtip. On paper, it's elegant. A longer, more efficient wing in flight but a smaller footprint on the ground. In practice, it adds actuators, sensors, locking mechanisms, and new failure modes. Every hinge, every hydraulic line, every electrical sensor is another inspection point. Airlines that buy the airplane will inherit extra schedule checks and new ground handling rules. That raises operation complexity and maintenance cost in ways that are easy to underestimate during sales pitches. Now, the part that stopped flight testing called the thrust link. This is a structural link that transfers engine loads into the pylon and the wing. In testing, thrust link cracks were discovered. A cracked thrust link is not a cosmetic issue, it's a primary load pass. Fixing it is required redesigning geometry and materials, validating new load pass, and retrofitting test airframes. That process is slow because regulators demand proof, analysis, lab tests, fatigue testing, and then flight validation. Each step takes weeks to months. When a primary structural item needs redesign, the whole certification schedule stretches. The final mechanics are straightforward but brutal. Boeing had planned deliveries and revenue recognition tied to certification milestones. When certification slips, revenue recognition slides too. Boeing booked a very large one-time charge in a single quarter to reflect the extra costs, rework, and deferred revenue. That charge is a blunt instrument. It acknowledges that the company will not get the cash flows expected to the original timetable. The knock-off effect ripples through supplier contracts, production rates, and airline fleet plans. Let's move through the timeline fast. The 777X program was launched as the evolutionary step from the 777 family. The original entry into service target was several years earlier than where things stand now. Testing began, the GE9X showed early borescope and temperature anomalies that required investigation, notably the thrust link cracks, forced pauses and redesigns. Each pause meant more testing, more inspections and more supplied work. A multi-year slip from the original plan. Why did this happen? 3 root causes boil it down: concentrated technical risk, optimistic scheduling, and regulatory caution. Concentrated technical risk because Boeing chose to keep the 777 commonality while adding radical subsystems. Optimistic scheduling because the company and suppliers assumed fewer unknowns that reality delivered. Regulatory caution because the FAA and other authorities are more conservative after recent high-profile certification controversies. Those three forces combined now the operational reality for airlines. When a carrier orders a new widebody, maintenance facilities, and financing around delivery windows, a multi-year delay forces airlines to extend leases on older aircraft, reshuffle crews, and sometimes reroute capacity. For a major customer that ordered hundreds of frames, the delay is strategic headache. Fleet modernization stalls, fuel efficiency gains are postponed, and network plans must be reworked. That's why some airlines reclassify or renegotiate orders when delays stretch on. Supplier stress is another hidden layer. When Boeing redesigns a thrust link or charges a pylon, retool, requalify, and sometimes hire new staff. Lead times for specialized forginnings, titanium parts, and actuators are long. A redesign can create bottlenecks across the supply chain, which then feed back into Boeing's production cadence, and part of the ongoing cash burn. Let's talk numbers without getting lost. A single large charge in one quarter signals two things. The company is recognizing a material near-term financial hit, and it's trying to clear the deck so future quarters are less volatile. But the headline charge is not the whole story. There are ongoing costs. Extra inspections, retrofits on early production airframes, slower production rates, and the opportunity cost of delayed deliveries. Those ongoing costs are harder to quantify in a single press release, but they matter to cash flow and to investor confidence. Here's a counterintuitive point. The very design choices meant to reduce airline disruption, keeping cockpit commonality, preserving 777 logistics, and fitting existing gates, increased Boeing's exposure to a few high-complexity subsystems. In other words, the strategy to be conservative and evolutionary ended up concentrating risk into a smaller number of novel components. When those components failed, the impact was magnified. That's the paradox. Evolutionary design can be risk-concentrating, not risk-reducing, if the evolution centers on a few unproven technologies. Compare briefly to the closest rival, Airbus's A350 family. The A350 was a clean sheet design with a different risk profile. It entered service early on and has been the go-to widebody for many airlines seeking long-range efficiency. One high-impact metric to compare is published maximum range. Range matters because it determines which non-stop routes an airframe can open and how much payload it can carry on the longest sectors. Their rival's published range is higher on some variants, which gives airlines more route flexibility today while Boeing's new entrant is delayed. That flexibility translates into revenue opportunities for airlines and market share for Airbus, while Boeing sorts out certification. Technical maintenance details that will keep engines awake. The gene and access advanced materials require new inspection techniques. Borescope inspections, thermal mapping, and AI-assisted anomaly detections are now part of the service entry conversation. Those techniques are not optional, they become part of the maintenance program until service data proves that parts are stable. That means more frequent shop visits early in the fleet life, and that raises direct maintenance costs and reduces aircraft availability. For airlines, that's a measurable operational penalty. Regulatory posture is the final lever. After recent industry events, regulators are less willing to accept incremental evidence. They demand phases inspections, more conservative test envelopes, and sometimes independent verification. That's good for safety, but it lengthens certification. Boeing must now demonstrate not only that a fix works, but that it will hold up across the entire service life under many more scenarios than originally modeled. That's why a redesign that might have taken months now takes a year or more to fully validate. Now a few practical implications for stakeholders. For airlines, Expect revised delivery schedules, high early life maintenance, and the need to hitch capacity with leased aircraft. For suppliers, expect renegotiated timelines, potential cost overruns, and pressure to meet new quality standards. For investors, watch cash flow, backlog health, and whether future charges are one-time or recurring. For regulators, expect a cautious-phased approach to certification that prioritizes service data accumulation. A quick technical aside for the engineers in the room. Fatigue in load-bearing links like thrust links is often a function of unexpected vibration spectra and local stress concentrations. When you combine a new engine with a new pylon geometry and a longer wing, you change the vibratory environment. That can create hotspots where fatigue cracks initiate. Fixing that requires either changing the local geometry, alerting material properties, or changing the damping characteristics. And each option has trade-offs in weight, cost, and manufacturability. Another operational reality: falling wingtips change ground procedures. Ramp crews must be trained to verify logs, maintenance crews must inspect actuators, and airports must accept that a new widebody has different taxi and gate constraints. These are small items individually, but they add up across a global fleet. We are not done with surprises. Early production airframes often require retrofits once a design change is finalized. It means some jets that were built to an earlier spec will need shop visits before delivery. Each retrofit is a production interruption and cash cost. The total number of retrofits and their cost is often not fully disclosed immediately, which creates uncertainty for both airlines and investors. Now the human factor. Boardroom decisions matter. Choosing an evolutionary path was a strategic call to reduce pilot training costs and preserve airline commonality. It was also a bet that the engineering challenges could be managed with the existing program structure. When that bet didn't pay off, the company had to make hard accounting choices. Take charges, slow production, and be transparent with customers. These are painful but necessary steps to stabilize the business. One more technical note: service entry inspections and AI-assigned bore scope analysis are not just stopgaps. They are investments in long-term reliability. If the industry learns faster and develops better predictable maintenance, the fleet will be safer and cheaper to operate over decades. The short-term pain may seed long-term gains in maintenance science. We are moving fast because the story itself is fast. A few components, a few test findings, and a cascade of financial and operational consequences. There is no single villain here, no single engineer or supplier to blame. This is a systems problem. And the physics of new materials all intersected. What to watch next? The pace of retrofit work on early airframes, the cadence of flight testing after redesign, and whether further changes appear in future financial statements. Also watch airline behavior. Will major customers stick with their orders, or will some reclassify or delay? That will tell you whether the market still trusts the program's long-term value. If you find this breakdown interesting, don't forget to put the like button on the video and press subscribe. See you in the next one.